Greetings of the day. I Asha K, Assistant Professor, Sai Vidya Institute of Technology, going to present in today's class DSP Algorithm and Architecture 7th Semester Elective Course 17EC 751. Now, in today's class, let us discuss about the Module 4 Implementation of Basic DSP Algorithms concept. First we have your introduction. Second topic we have here is the Q notation and FIR filters, representation using the assembly level language program, IER filters, interpolation filters, and the last one is decimation filters. These are the topics of interest in this particular module for implementation of basic DSP algorithms. In introduction, we have here the DSP algorithm which is written to implement the certain algorithms of the processor. However, the programs that we are writing here, it is combined with input-output lines to create the application that work with a specific hardware. We have the concepts such as Q notation representation of the numbers, FIR filters, IER filters, interpolation filters, and decimation filters. The first topic that we have here for the class is Q notation. The DSP algorithm implementation deals with signals and coefficient. Signals are represented as x of n and coefficients are represented as h of n. To use here a fixed point DSP devices efficiently, what we have to do here it is we have to represent the filter coefficients and signal samples using fixed point 2's complement representation. For example, when we have n is equal to 16, the range of the numbers that we are representing 16-bit data here is minus of 2 to the power of n minus 1 to plus 2 to the power of n minus 1 of minus 1. Typically, the range for n is equal to 16, we have here minus 32,768 to plus 32,767. Typically, all the filter coefficients that we are using in the DSP algorithm and DSP processors are fractional numbers. Q notation example. The Q notation specifies the number of fractional bits. Example Q7, Q15, Q3, Q8, etc. We'll discuss one Q7 example. If the number is given binary, say it is represented like this, if this number has to be represented in the Q7 representation, let us consider the number given was 10101 followed by 3 zeros and followed by 3 more zeros. If the number is given as this, that 0, here I'll be having 4, say here I'll be having 5, here I'll be having 0. 0540 hexadecimal number. I'm converting this into binary, and after converting this bit into binary, since I need to represent this in the Q7 notation, after 7 bits, that is 1, 2, 3, 4, 5, 6, 7 bit, put a decimal point, then easily this number is converted into Q7 representation. So here this before the decimal point, whatever the numbers that we have, that represents the fractional bits. After the decimal point, this represents the whole part plus sign of the number. The MSB signifies the sign of the number and also the decimal point representation. So this is decimal point. After 7 bits we are representing here decimal point. This is called as Q7 notation. In case of Q15, after 15 bits, that is starting from here to here, you will be having the 15 bits, total of 16 bit. After 15 bit, put the decimal dot, decimal point that represents the Q15 representation. If it is Q1 representation, after 1 bit, put a decimal point, convert that into the fractional part and the integer part, then you will get the Q1 representation. So the commonly used notation in DSP implementation is Q15. In Q15 representation, the least significant 15 bit represents the data. So here in the processor where 15 bits are used to represent the number, the Q15 notation uses the most significant bit to represent the sign of the number, and the rest of the bits represents the value of that particular number. And here in general for Q15 numbers representation, n is represented as B15, B14, B13 till B0 bit. Now n is equal to, since the 15th bit, that is the last MSB bit represents the sign of the bit, minus of B15 2 to the power 0 plus B14 into 2 to the power minus 1 till B0 into 2 to the power minus 15. So this B14 bit to B0 bit represents the fractional part, and the first bit, the MSB bit, represents the sign of the number in case of Q15 representation. The range for Q15 representation is minus 1 to 1 minus of 2 to the power minus 15 is the range of representing the numbers in Q15 representation. Example 1. What values are represented by the 16-bit fixed point number n is equal to 4000 hexadecimal in Q15 and Q7 notation? So first what we have to do here, it is convert the number into binary. That is, for n is equal to binary representation 0100 followed by, we have 4 zeros here again, 4 more zeros for the 0th bit and remaining 4 zeros for the remaining 4 bits. Then whether it is Q15 or Q17, that is based upon where I am going to insert this decimal point. If the decimal point after 7 bits, 0, 1, 2, 3, 4, 5, 6, 7 bit, after 7 bit if I am going to insert the decimal point, say here again I am writing the number, I have here 000, I have here 000. If I am going to insert this decimal point after 7 bit, that is 4 here it is this is the decimal point value. Then represent this data again. If you represent that data again, this will be 0th bit, 1st bit, 2nd bit, 3rd bit, 4th bit, 5th bit, 6th bit and 7th bit. In case of Q7 representation, the value of this number is 128, that is positive 128. Similarly, if I convert this number into Q15 notation, after 15 numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. After 15 bit, put a decimal point and convert this into the Q15 notation. In Q15 notation, that is 1 into 2 to the power minus 1. This is nothing but 0.5 plus 0.5 is the answer in case of Q15 notation, and in Q7 notation it is plus 128. Multiplication of numbers represented using Q notation is important for DSP implementation. So we are learning now multiplication of these two numbers. The figure shows the typical cases encountered in such implementation. I have one n1 number, I have another n2 numbers. I am performing here signed binary multiplication. The result is n3. Say if n1 is of 16 bit and n2 is also of 16 bit, the n3 that we are going to get may vary based upon what type of notation I am using. I may be like multiplication of 16 bit, you will be having the double the bit. Here, since it is the double the bit, say if Q0 representation is used, if one number is Q0, another number is also Q0, the resultant is also Q0. If one number is Q0, another number is in Q15 representation, the result will be in the Q15 representation. If number is in Q15 representation, if N2 is in Q15 representation, the final result will be in Q30 representation. Now consider the program to multiply Q15 numbers that is n1 into n2, that is equal to multiplication of n1 into n2, where n1 into n2 are 16-bit numbers represented in Q15 notation. Whereas the product will be generally in the terms of, that is Q30 notation, but again we are altering, we are adjusting or rounding off the result to Q15 notation only with the help of the assembly level language program. To use the memory mapped register, we have a directive .mmreges, and this shows the data section of the ALP program, that is sequential locations for the data. We have the first data, that is N1, it is of .word 4000 hexadecimal. If I represent this in Q15 notation, that is equal to 0.5. Consider another number N2, it is also .word 2000 hexadecimal. When I convert this into Q15 notation, the value for this is 0.25. I am allocating the space of 10 hexadecimal to the product n1 into n2, that is the space for n1 into n2. And dot text part is the directive part, where dot reference underscore c underscore int00, and also we have a sectionalized memory locations for dot vectors representation, and we have a reset vector for this Q15 numbers multiplication with the label reset b, that is equal to underscore c underscore int00. It is called as the reset vector. No operation, which is used to introduce the delay, again no operation, and beginning of the dot text code with underscore c underscore int00, that shows the ALP program is going to start. Store memory immediate value, that is n1 to AR2, and now AR2 is pointed to the n1 Q15 number. Load star AR2 plus 2 comma temporary register. Now the temporary register is having the data of n1. That data of n1 is nothing but equal to 0.5 in the Q15 representation. Now multiply star AR2 plus comma A. So when I start multiplying, now AR2 is pointing at the second number, that is N2. Already in T register we have N1. When we multiply the content of T register with the auxiliary register and store the result in the accumulator register, the accumulator is a 40-bit register. It consists of the multiplication of N1 and N2 in Q30 notation. Now we are rounding off the result to Q15 notation with the help of an instruction add immediate value 1, shift that value 14 times, and then add with the accumulator A and store the result in the accumulator. This makes the Q30-bit representation to Q15-bit representation of the answer N1 into N2. Then store higher word of the accumulator A, shift 1 bit and store that in the location star AR2. No operation, and dot ends the program. It's a directive to end the program. AR2 will have the result, that is multiplication of N1 into N2 in Q15 number representation. Problem 1. Determine each of the following 16-bit numbers represented using Q notation. The number given here is 4400 hexadecimal. Represent this 4400 hexadecimal in Q0, Q15, Q7 and Q1 representation. Consider the number 4400 hexadecimal, convert that into binary. Each number represents the 4-bit binary value, that is 0100, 0100 and for the next bit 4 zeros and the next bit 4 zeros. In case of Q0 number representation, we'll be having here the number as it is, because after 0 number, if I am going to put a decimal dot, it's of no meaning. Hence the Q0 number representation, convert this hexadecimal value 4400 hexadecimal to an decimal value. If I convert that into a decimal value, for that particular purpose, we have to represent the position of this particular number. This is at the 0th position, 1st position, 2nd position, 3rd position, 4th, 5th, 6th and 7th, 8th, 9th, 10, 11. Here it is 12, 13, 14, 15. When I convert this into decimal, 1 into 2 to the power 14 plus 1 into 2 to the power 10 is the answer. 1 into 2 to the power 14 is nothing but 16,384, and 1 into 10 to the power 2 to the power 10 is nothing but 1024. The final answer 17,408 is the Q notation, that is Q0 number. Consider the same number, that is 4400 hexadecimal, and we all know that how to convert this into binary. Write it in binary representation. After writing this in the binary representation, say count from the least significant bit side 15 numbers. Here it is 0, say first one is first bit, second bit, third bit, fourth bit, fifth bit, sixth, 7, 8, 9, 10, 11, 12, 13, 14, 15. After this particular bit, put a decimal point here and convert this number into like integer part and fractional part. Here only one MSB is there, so this results in 0 into 2 to the power 0. That 0 into 2 to the power 0 is like 0 itself. Next, 1 into 2 to the power minus 1 I have. This is minus 1, minus 2, minus 3, minus 5. It goes on like this. Since I don't have number 1, so I'll stop here itself. So 1 into 2 to the power minus 1 plus, see here we'll be having 1 into 2 to the power minus 5. When I convert this, 1 by 2 plus 1 divided by 32. Here it is 0.5 plus 0.03125. I'll be having here 0.53125 as the number in case of Q15 representation. Similarly, the number 4400 hexadecimal, that is represented in binary, that is this is the binary representation after 7 bits. Say here I am having after 7 bits. What we are going to do here, it is we are going to insert a decimal point, that is third bit, fourth bit, fifth bit, sixth bit, seventh bit. Put one decimal point in this case. After inserting the decimal point, what you have to do, convert this number into integer and fractional part. Here the position for this particular number, here it is 0, 1, 2, 3, 4, 5, 6, 7, 8, and at this particular side we'll be having minus 1, minus 2. Since we don't have logic 1, the binary bit 1, hence it is neglected. So when I convert this into like hexadecimal, that is integer part, I'll be having this 1 into 2 to the power 7 plus similarly, so I'll be having 1 into 2 to the power 3. Say here it is 1 into 2 to the power 7 is 128 plus 2 to the power 3 is we'll be having 2 to the power 3 as 8. So addition of this, we are going to get 136 number in Q7 representation. Say we have to represent the same number using Q1 representation, that is 4400 hexadecimal. Write that in the binary representation, and after writing that in the binary representation, after one bit put a decimal point, then convert this into, that is integer part and the fractional part. It is almost same as like Q0. One here it is no decimal point at all, but here we have one decimal point. For this particular number, if you write the position, that is 0th position, first position, second, third, fourth, fifth, sixth, 7, 8, 9, 10, 11, 12, 13 and 14, and convert this into an integer and fractional part, you'll be having 2 to the power 13 plus 1 into 2 to the power 9. The answer for this we are going to get is 8192 plus 512, together 8704 is the final answer. In Q1 notation. Problem number 2. What are the values represented by 16-bit number, that is 4000 hexadecimal, in Q15, Q7 and Q0 notation? Consider the number. First write that number in the binary form. 0100 followed by 0 followed by zeros and followed by zeros. If I put a decimal point after 15 numbers, 15 binary numbers, and convert this into the fractional and integer part, we are going to get 1 into 2 to the power minus 1. This is nothing but 0.5. Positive 0.5 is the answer. Again represent the same number in binary, but we are going to insert the decimal point after 7 bits. 4 plus 3, 7 bit, put a decimal point. If you convert this number into like integer and fractional part, this is 0th bit, 1st bit, 2nd bit, 3rd bit, 4th bit, 5th bit, 6th bit, 7th bit, 8th bit. Here it is minus 1, minus 2, minus 3, minus 4, minus 5, minus 6 and minus 7. The answer here it is 1 into 2 to the power 7. All others become 0. The final answer is plus 128. The same number, if it is represented in Q0 notation, the number as it is, that is 10100, 000 followed by 000 followed by 000. For this particular number, write the position 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 and this is 15. If you convert this into integer part, 1 into 2 to the power 14 is the answer. Here it is represented as plus 16,384 in Q0 representation. To prepare the content in this particular presentation, the textbook referred is this and the reference books referred are the following. Thank you all.